Hello everyone, I'm Linxi Zhang and my partner is Changlin. We will introduce hierarchical CPU scheduler for multimedia operating system. Firstly, let's talk about the motivation. As we all know that over the past few years, computing, communication, and video compression technologies have advanced significantly. Their hierarchic advance have made the bandwidth and the storage space requirement of digital video manageable, and thereby have enabled a large class of multimedia applications, such as video conferencing, distance learning, and so on. Since digital audio and video can be appropriate, meaning only when presented continuously in time. Such applications impose real-time requirements on the underlying storage, transmission, and processor subsystem. Especially, they require an operating system to allocate resources such as CPU, I/O bus, disk, and network bandwidth in a predictable manner, as well as provide the quality of service guarantee. Thus, we can note that whereas application classes in multimedia system need different scheduling algorithms. The second point is that the author designed the hierarchical CPU scheduling supports different scheduling algorithms for different applications and protects application classes from one another. Next, let me introduce a framework for hierarchical CPU scheduling. In the framework, the hierarchical partitioning requirements are specified through a tree structure. Each node in the tree has a weight that determines the percentage of its parent node's bandwidth that should be allocated to it. Furthermore, each node has a scheduler, whereas the scheduler of a leaf node schedules all the trees that belongs to the left node. The scheduler of an intermediate node schedules its child node. The second point is that these trees in the system belong to actually one leaf node. Each leaf node represents an aggregation of trees and hence an application class. In the system, each non-leaf node in the tree represents an aggregation of application classes. Thus, we can get the third point is that each non-leaf node represents an aggregation of application classes. Here is an example scheduling structure. The root node has three sub-nodes: hard real-time, soft real-time, and best effort, with 1, 3, and 6 respectively. The bandwidth of the best effort node has been further divided equally among leaf nodes, user 1 and user 2. Furthermore, whereas the soft real-time and the user 1 leaf nodes employ a scheduler that fairly distributed the CPU allocation among its threads, the hard real-time and user 2 nodes have EDF and time-sharing scheduler respectively. In this page, there are 4 requirements of scheduling at intermediate nodes. The first one is that allocate the residential bandwidth fairly among its subclasses. As I showed previous page, that example, if there are no eligible threads in the hard real-time class, then its allocation should be participation between the soft real-time and the best effort nodes in the radio 3 radio 6. The second point is that since the combinational requirements of tasks may not be known previously, the scheduling algorithm should not assume a priori knowledge of the time duration for which a task executes. asterisk before it's blocked. The third point is that to support hard and soft real-time application classes, the scheduling algorithm should provide bounds on minimum throughput and maximum delay observed by nodes. Furthermore, for the bounds to be useful, they should hold its realistic computing environments in which interrupts may be processed at highest priority. The fourth point is that to feasible in general-purpose operating system, the scheduling algorithm should be computationally efficient.
Now it's my turn to introduce you the SFQ algorithm. The RF means the weight of thread F. It kind of reflects its importance. And QF is the quantum of thread F, and AOF is the length of QF in units of instructions. And AQF is a thread request time, and the SF is start tag, FF is finish tag for thread F, and VT is virtual time at time t. I think there are three equations that are very important and very unique in this algorithm. Firstly is that the author define a virtual time VT. It's initially 0 and it's the start tag of the thread in service when CPU is busy at time t, at the maximum finish time when CPU is idle at time t. Also author define the start tag of thread F, which is defined by the maximum time of the requesting time of the process and its last finish time. And the finish tag is initially 0, and it equals the start time plus the quantum length divided by its weight. He shows that his SFQ algorithm has the following properties. One is a fair allocation of CPU, regardless of the bandwidth. So the fair list of the CPU is defined by this equation, the equation on the left. If this means during a time period between T1 and T2, the running time for the process F and process M to divide it by their own importance. If this whole equation equals 0, then that means the process F and process M receive the same fairness. And the author proves that his algorithm, the value of this equation is less than this value, and he said that this value is smaller than any algorithm present at his time. But this is fairly a very old paper, so I don't know whether this is a very small value, I mean, for the compare with the algorithm now. And also, he mentioned that another property is that there is no need of priori knowledge of content. It's just because that the start tag keep increasing itself. This is an example showing the result of his SFQ algorithm, where process A and B, they have a weight of 1 and 2. And this example clearly shows that both A and B, they have the same fairness. But I think what is not good about this paper is that it didn't prove it mathematically. He just showed one example. which I think is not that good. The third property of this algorithm is that it provides bounds on maximum delay incurred and the minimum throughput achieved by threads in a realistic environment. But to derive this bound, the variation in CPU bandwidth has to be quantified, and it can be quantified as two models. It can be quantified as a fluctuation constraint server, and here's the bandwidth, throughput, and the execution complete time of this model. Model as exponentially bounded fluctuation server, and here is its bandwidth, throughput, and execution complete time.
In this implementation part, firstly, I want to talk SFQ scheduling is used for intermediate nodes, that is, no left nodes. And for the left nodes, it can use any algorithm, not just can use SFQ. In this implementation, each node has the wait, start tag, and finish tag. And each no-left node has a list of children nodes, list of runnable children nodes, started by start tags, virtual time of the time nodes having the minimum start tag. And for the left nodes, each left node has the pointer to a function. For the implementation, there are some functions are needed. You can see that in this page. And the other point is the priority invention. Observe that the threads in a system may synchronize or communicate with each other, which can result in priority invention. And there are two solutions. First one is that not them between classes. The synchronization between those belongs to different classes is not desirable, since that may lead to violation of QoS requirements of applications. The second solution is that only within the same leaf classes. There are also two details for two different situations. The first one is that if it's rate mononic, it can be run in this way, use priority inheritance. The second one is that if SFQ situation, it can be run in that way, transferring weights of blocked to the blocking thread. And this picture shows the quality of service manager. You can see that the applications will specifying their QoS requirement to the QoS manager, which would determine the resources needed to meet the QoS requirements of the applications. And it also can decide the scheduling class the application should belong to and create a class if it does not exist. Also, it can allocate the resources to the application and move it to appropriate class. It would also dynamically change the relative allocation of different classes so as to effectively meet the requirements of the applications that may coexist at any time. In this page, we can see that the framework for the experiment. And after the experiment, we can go to the conclusion that SFQ can achieve fairness even in the presence of dynamic variation in weight assignments. Let's talk about something about the related work. The earliest known fair scheduling algorithm is weighted fair querying, the WFQ, that was designed to emulate a algorithm-weighted round-robin server in which the server received by each third in a round is infinitesimal and proportional to the weight of the third. But it's not fair when bandwidth is fluctuated, and it also requires length of quantum to be known per pair. It's also computation of round number expensive. Then the next is fair querying based on start time. FQS was proposed in paper which in the reference. That's its aim to make WFQ suitable for CPU scheduling when the quantum length may not be known per pair. It doesn't provide fairness when the bandwidth fluctuates. The next one is the self-clocked fair querying ECE578. It was designed to reduce the computational complexity of fair scheduling algorithms like WFQ. It's increasing order of finished text and larger delay guarantee than SFQ. The next one is lottery scheduling. It fairness but only when the large time intervals, and it also supports hierarchical participation, but it's only one scheduling algorithm, and it also has a problem that is computational overhead. The next part is conclusion. After the authors demonstrate, and we can know that the framework enables coexistence of heterogeneous schedulers, and also the framework can protect application classes from each other. The last point is that the framework doesn't impose higher overhead than conventional time-sharing schedulers. You can see that there are some reference for the paper we read. That's all. Thank you for your listening.